Hello, in this video I want to make a list of strong bases, weak bases, and third category, bulky bases. And it's important to be able to identify what kind of base you have in these alkyl halide elimination reactions. By now, you should be very familiar with substitutions of alkyl halides. And yes, a base can act as a nucleophile, and you could get a substitution product. But for this particular video, though, I want to focus only on elimination and deciding or learning how to decide whether a reaction is going to go via E1 unimolecular or E2 bimolecular. Let me just put here a statement about elimination reactions. In an elimination reaction, what do you remove? What do you eliminate? You remove two things, beta hydrogen and the leaving group. In this case, it's going to be a halide. And you're going to remove those two things from an alkyl halide using a base to make what? To make alkenes. It could be one alkene, but often you're going to have a mixture of alkenes. Okay? If you could identify that you have an alkyl halide, and you can identify you're reacting with a base, and particularly what kind of base, you will make most likely an alkene or a set of alkenes. Let me show you the first example. 2-bromopropane plus, and we're going to use just a general base, a generic base. I'm not going to tell you the identity of that base. We'll do that later when we categorize these. But in this case, I want to use an anionic base. And let me draw you the mechanism. There's a beta hydrogen on either side of the alpha, because we have beta carbons on either side of the alpha carbon. The alpha carbon is the carbon that's connected to the halide. Remember that I said that we eliminate the beta hydrogen, and the way that happens is the base grabs one of these beta hydrogens, the bond collapses to make the double bond, and you kick out bromine. In this case, the mechanism says that there's only one step. It's all concerted, these three green arrows. So what do we have? We have the base that picked up a hydrogen, particularly a proton, and we kicked out the leaving group, the Br-. Since there's one step, that step has to be the slow step, which is called the rate determining step. The slow step determines the overall speed of the reaction. This reaction is called bimolecular. Okay. Let me write it in purple. Bimolecular, meaning two, because two things control the rate of this reaction. Rate equals K times the concentration of the alkyl halide. Sometimes the textbook calls that the substrate, and the concentration of the base. Two things. Hence, this reaction, the way that it proceeds, how I draw the mechanism, is called E2. It's an E2 mechanism, 2 for bimolecular. Again, we'll talk about the base specifics in just a bit. I want to show you the two examples, the E2 first, and then the E1. For the E1, let's again use the same alkyl halide, but now for E1, the base either is not strong enough, or actually, Yeah, the base is not strong enough. So what happens here is that it waits and waits and waits until the bromine pops off. Usually, you heat the reaction to have that happen. Oh, here we have the plus, carbocation, and the leaving group, Br minus. Okay, what's important here is that we have a carbocation made in this mechanism. You know, we're going to end up with the same product. We're still going to end up with an alkene that eliminated the beta hydrogen and the bromine. The base we're going to use here is going to be neutral though, okay? And where's the beta hydrogen? We still have the same alpha carbon and the two beta carbons. So just remove one of these hydrogens off of the beta carbon with the base. This comes in, picks up the proton, this collapses. So you see that the leaving group leaves before the base grabs the proton. That's different than what we saw originally. Right, in an E2 mechanism, the base grabs a proton, the double bond is made, and the bromine leaves, all at the same time. But here, they're separated. Plus H base. We started out as a neutral base, so when it grabs a proton, this actually becomes positive. Right, you increase the charge. Here we started out with a anionic base. We grabbed the hydrogen and became neutral. But look at the difference. There are now two steps. It's the first step that is called the rate determining step. And because there's only one molecule involved in the rate determining step, this is called unimolecular. You see the difference? Here, to get through the rate determining step, I need two molecules, and those two molecules determine the rate. Over here, to get through the rate determining step, I need only this alkyl halide. That's why for the rate equation, you only worry about the concentration of the alkyl halide. This process is E1 for unimolecular. Okay. Chances are this is review for a lot of you. You're here really to categorize bases. What's a strong base? What's a weak base? What's a bulky base? You want to know how to do that because strong bases proceed via E2. Okay, it's a strong base. It doesn't want to wait. It grabs a proton, gets the process done. Weak base hangs out until you get a carbocation. Okay, and now it's has motivation to grab this proton. It's a weak base. It really doesn't have, I guess, the motivation, the driving force to grab that proton until there's a carbocation there. That's important that we form a carbocation. Unimolecular processes, whether it's E1 or SN1, go through a carbocation. Okay. So let's categorize. How do we know what's a strong base and what's a weak base? The first set we're going to use, or we're going to describe our strong bases. Okay, the first set is the oxide bases, the ones with oxygen. The tricky part is you could see these oxide bases in several different forms. The most popular is NaOET. What is that? Well, that's the same as, you got to think of this as the counter ion, and then in solution it separates. And when it separates, there's your anionic base, that O minus. ET stands for ethyl, and you have that. It's analogous to what? It's analogous to NaOH. You know that NaOH is a base, but when you draw the mechanism, you don't worry about the Na, you just worry about the OH minus, right? So you could have ethoxide, hydroxide, even methoxide, CH3O. Let me write it down. CH3O minus. I'm drawing the lone pairs because you need those lone pairs when you draw the mechanism, right? It's the lone pair that's making the bond to the proton in both cases, strong base and the weak base. Okay. Those are your oxide bases, and those are typically the ones that people use. But there's also nitrogen bases. There's NaNH2. NaNH2 is a strong base because you have this NH2 minus, right? Strong base. Do you remember in the acid-base chapter, your professor might have said weak acids give strong bases. So if I made this into an acid, the conjugate acid, that conjugate acid, NH3, is a weak acid. It has a pKa of 36. So that NH3 weak acid gives me a strong NH2 minus base. Okay. All right, so that's good. Another one is, I know I'm using sodium as a counter ion. It doesn't have to be. It could be lithium. It could be potassium. Any +1 counter ion would work. Lithium, sodium, potassium. Okay. What's NaH? Well, do the same trick. Separate out the plus Na, and you're left with a minus species, hydride in this case. Hydride is a strong base. There are two carbon-based strong bases. One is called N-butylI, N-butyl lithium. So here the counter ion is lithium, but you know a butyl group. A butyl group looks like this, but it's the anionic form, CH2 lone pair minus. That's a super strong base. You know why? Because that strong base came from a very weak acid. Butane is a weak acid, right? Carbon, the hydrogen and carbons are not very acidic. And then you have your lithium. You could draw it or you don't have to. When you do the mechanism, you're drawing the mechanism error from the lone pair. And then the last one is the alkyne anion. How do I want to draw this? This might look familiar if you've gone through the Alkyne chapter. The way I have it ordered, actually this chapter comes first, or this unit comes first. But anyway, it's still the same idea. You have a C minus, C anion, which is a strong base. This is called an alkynyl anion. Okay, that will strip off a beta hydrogen from secondary or tertiary alkyl halides. Don't worry yet about the type of alkyl halide. Just know that these are all strong bases. And then when you react these strong bases with an alkyl halide, your mechanism will look similar to this. One step. Okay, strong bases. The weak bases are even easier. You notice that all these strong bases have anions, negative charge atoms. The weak bases are all neutral. And let me show you some common weak bases that we can use for eliminations. The weak bases typically are water. And I'm going to draw the lone pairs because, again, when you have this elimination, okay, now we're going to use a weak base. You're going to use the lone pair to grab the proton. Okay. Oh, by the way, why don't I just put here, when you have a strong base, if you have the alkyl halide plus strong base, okay, you'll get the alkene, but this proceeds via E2. It will go ahead and grab that proton right away. One stepper. So remember that. That's your connection. Strong base, E2. Weak base, E1. Okay. So weak bases eliminate alkyl halides. Oh, my spelling. via E1. Because it's a weak base, it's going to hang out until a carbocation is formed. Water, any alcohol, methanol. You notice that these are neutral. Well, for a strong base, we had an N minus, N minus. So by analogy, if we neutralize it, NH3 minus, NH3, neutral, that's a weak base. Or sometimes they'll have an R group, CH3 and H2. That's a weak base. Those are typically the weak bases. A lot of these are liquids. So if you want the elimination to proceed in an E1 fashion, you just dissolve it in water, the alkyl halide, or dissolve in methanol, or dissolve in liquid ammonia, and you heat it. And then the reaction will proceed via an E1 mechanism. Weak base, heat it a little bit to get the carbocation made, and then make the alkene. Because of that convenience, that all you have to do is heat in solvent, a lot of times E1 is considered solvolysis. SOLVOLYSIS, solvolysis. Maybe you've heard of that term before. Solvolysis is typically known as an E1 process. For some textbooks, it's also an SN1 process. Okay, you could heat up an alkyl halide with any of these solvents and it can undergo substitution via a unimolecular process. That's the most important thing. Solvolysis can be think of the unimolecular processes E1 and SN1. Okay. All right. There's one last category. Well, let me just go through the two examples now that we know how to identify a strong base and a weak base. So if I have this alkyl halide, okay, same alkyl halide we had before, and let's say I reacted with NaOET versus reacting it with what? Let's use methanol, CH3OH. The thing is, for this alkyl halide, there's really only one type of alkene we can make, right? Either the double bond to the left or to the right, and they're both the same molecule. So what's the point? The point is, you may be asked on an exam, draw the mechanism. If you're given this reaction, you have to draw an E2 mechanism. This goes via E2. And if you're given methanol, and yeah, I'll put heat, okay, you're going via an E1 mechanism. And don't forget E1, you go through the carbocation. Okay. Weak base. One last category, and it's a special type of strong base, and it's called a bulky base. Bulky meaning crowded, heavy, I guess. Let me show you some examples. These are interesting. They're specially made to do an E2 reaction, but to give us a different product than what we expect. But let me show you some examples first. Before I show you the examples, bulky bases, there are also strong bases. Therefore, they're going to proceed via E2. Okay, via E2. But there's a reason why you want to use a bulky base rather than just a regular strong base. Let me show you the reason why. Actually, let me give you the list, and then I'll show you how to use a bulky base to get a different product than what you expect. The bulky bases, the first one is called KO superscript T BU. This is called potassium terpetoxide. Potassium for the K, the T, tert, for tert, and then we have a butyl oxide, or really it's butoxide. Ugh, that's a mouthful. You could also see it written, well, let me show you the line structure. Potassium is K+, but in the mechanism, you don't need to use a K+. You need to use the O-. That's what's important in the mechanism. Tert-butyl, you know, it's like the crow's foot. Now, there are many ways you could see this. They could draw it out for you. They could give you the name. They could give you the, like the chemical formula, or not the chemical formula, but the abbreviation. Or they could give you the condensed structure. K, O, C, and your 3 methyl groups. Okay, right? Those two are the same. These 3 are the same. Bulky because it's crowded. Let me give you another very interesting one. It's called DBU. Oh no, let me give you one that you're likely to see first. It's LDA. That's lithium diisopropyl. My spelling. Diisopropyl. One word amine. Look how crowded this one is. N, 2 isopropyl groups. We have a negative charge for the nitrogen, and then lithium, Li, okay, as a counterion. That's a bulky base. And there's one, it's rarely taught, but I like it a lot. I've used it, DBU. And DBU looks like this. It's a 7-membered ring. Oh, I messed up already, I think. That's 7. 1, 2, 3, 4, 5. Oh, good, 7. And then it's fused to a 6-membered ring. And your lone pairs are there and there. The basic nitrogen is this one, the one with the double bond. Anyway, this is DBU. This has a long name. 1,8-di-aza bicyclo un for the U dec 7-ene for the 7-membered ring undes 7-ene. Don't worry about the name. It's DBU though. Okay, those are your 3 bulky bases. Why would we use that goes E2? If I really want E2, why don't I just use one of these easier bases to memorize? That's also E2. Because let me show you what a bulky base can do for us. If I have this alkyl halide, okay, it's a little more complicated. And we have, again, 2 beta carbons, one on the left, one on the right. If I reacted with the normal strong base, let me use NaNH2. We haven't used that yet. We're going to proceed via E2 because this is a strong base. And I say that often when I give an exam. My students like to identify what kind of base, and then they remind themselves what mechanism when they're going through the mechanism. Obviously, if you're just drawing the product, for most cases, it doesn't matter whether it's E1 or E2. Okay. The major product is making the double bond to the right, towards the more crowded beta carbon. You might have heard this as the Zaitsev product. And for most reactions, elimination reactions, you are following Zaitsev's rule, which says that you form the more stable double bond, the more substituted double bond. You notice that we did not go to the left. What's underneath here? Let me just... If we go to the left, we get a different product. Same alkyl halide, and now let's use one of our bulky bases. The one that's most popular is potassium terpetoxide. It is still E2. It is still a strong base, But now this is a strong, bulky base, crowded base. Look what happens to the major product. The major product is not this anymore. We have to form the double bond on the less crowded side. On the less crowded side, because the base is too big to grab a proton off of the beta carbon that's crowded. So we're still forming, like in the first case, a double bond between the alpha and the beta, but now the beta we're using is on the left. This is called the Hofmann product, and it's, I want to spell this right, 1F, and it's interesting because you're making the less stable double bond. The less substituted double bond is the less stable double bond. But it's the one that's made because it's so hard for that crowded base to grab the proton off of this beta carbon. So you're making the less substituted. Now there are reasons why, when you have an alkyl halide, why you may want the Zysef product. And there are other reasons why you may want the Hofmann product. It just depends on, what you want your molecule to do. Maybe it's more reactive when the double bond is on the end. So this is a less substituted double bond. Okay? That is all that we need to know for the bases, and hopefully that clarifies your understanding of how to pick the strong base, what is a weak base, and what is a bulky base, and how those are used to synthesize different alkene products.